Oh boy, it looks like I had my hat on, coming in out of the cold. Didn't know it was snowing here, slush. Sneakers are on the radiator, drying out. Anyway, this is going to be a video on bridging the great divide from pre-cal to calc. So we're in a calculus class, and I'd like to show you some things that I like to do at the pre-cal level to introduce some concepts. And because I didn't have many of you, I'd like to share just a couple of situations that might help you get a better understanding of rates of change of polynomials. The last video was about sinusoids. We talked about the change in radian measurement with respect to the change in the altitudes of a sine function in a unit circle. Again, repetition's our friend. Just looking at it once might not be enough in terms of generating movement towards a stronger, a deeper understanding of what's going on with that calculation. And so we've done some of this work, but bears repeating, I think. So let's look at a polynomial. Let's get started there. And then we want to get into the geometry of the problem and see how polynomials are really numerical tugs of war. So let's make sure that the video is pinned proper. There a little higher. There, that's pretty good. That's pretty good. Hopefully I'll check it from time to time. So I'm just looking at throwing a couple of numbers in. Obviously, the most critical number here is 0, the easiest number to work with. So we put a 0 in, we get 7. We put a 0.001 in. I don't know what 0.0001 cubed is, but I think if this is 4 decimal places, I think we're looking at 12, and then multiplying it by -2. And something with 12 decimal places is pretty small. So I don't think it's changing much here. And because I don't have much space, I'll say, very little change, very little change. VLC, very little change. I do know how to square 0.001 times 4. So, if I do that, I'm going to get 0.0008 as 0001. I could check that. I think I'm pretty right about that. And you know what? That's pretty small too. It's about 10,000 times, roughly, smaller than the next number, which is -4 times 0.0004. We've talked about this in class, and again, if you see the number 7 change over here, email me. Okay, I think we want to talk about that, and let's have a conversation. So just keep your eye on 7, and if this 7 starts to change for you, just email me. No problem. Don't worry about things. Everything's fine. Just email me though. Okay. So where's the real change coming from? The real change is not coming from this term locally, this polynomial locally. That's dictating change, and we've talked about that. That actually is the slope of the tangent. It's right there. That's a little snippet of what this graph's going to look like. Okay, and obviously if I divide by 0.0001, I think we can start to see that this is trending towards that rate of change. And the more zeros I put into the decimal, the closer I am to that value. All right, and that's where we start moving towards the concept of a limit. In this case, the limit of the rate of change at x equals 0. Now, as we move away from x equals 0, as numbers get bigger, and we'll go in the positive direction. It's easier to calculate positively than negatively, I think. We go to the number 10. You got -2,000, you got a 400, you got a -40, and you got a 7. This obviously is dictating the end behavior. I almost think we should, in math, start to rewrite it in the other direction, because this now gives us a feeling, just a little feeling for the numerical influences. The biggest influence is a 7 at 0. We know we're going down at 4 to 1. And this is going to bring us a little bit in the other direction, near 1, I guess, right? I mean, 4 times -4 times 1 and 4 times +1 kind of already kind of offset each other. So this is quickly overtaking this, very quickly overtaking this as soon as I get past 1. So it looks like this critter is going to come right back up for just a, a tendency. Now, whether or not we get a local max or a min, that's what the calculus study is about. But there is a tendency. But eventually, we know that this is taking over, and we're talking down. Okay, so this is what we would analyze in a calculus class: maximums, minimums, things like that. Thinking with negative numbers, it's a little harder, but not much. I mean, if you put a negative number in, -1 times -4, then yeah, a continuation of up, right? Negative number squared or positive times 4, still moving up, right? And negative, 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 up. So we know this critter does that on this side, and then we analyze more carefully. Does it have a local? Does it have a min? Does it have a max? And we certainly know it's got a point of inflection in here. We can see concave up to concave down. And I want to look at that a little more carefully on the other board here. I put some things on the board that I hope I can capture and discuss in a way that makes a little more sense to you as to what's going on. Okay, so did I cover what I wanted to cover here? I believe so. Okay, so let's take a look at that cubic a little more carefully. Let's dive into it a little more deeply. All right, so let me pin the video. I'm capturing, let's see. Yeah, most of what I want can go here for now. All right, so this is the graphing form for a cubic. Okay, and if you want to try to understand that, it's based on completing the cube and some algebra. Can get that formula or that calculation. Changing what I'm doing here is I'm changing ax cubed plus bx squared plus cx plus d. I'm changing that into something that allows me to envision. And we'll talk about this stuff in a moment. Okay, but what does all this stuff come from? It comes from geometric shapes. I think the entire study, honestly, is really born from looking at geometric shapes. I mean, think of your language: linear, quadratic, quad, four-sided, right? Rectangles, cubics. Okay, so let's talk about the cubic function. Just cubing, -2 times -2 times -2, get you -8, -1 times -1 times -1 gets you -1. 0 times 0 times 0, 0, 1 times 1 times 1, 2 times 2 times 2. Okay, and a moment ago I had what I wanted us to consider, which is y equals minus, let's put the full thing together. I'm looking at y equals x cubed minus 2x is what I want to look at now, which is actually in this graphing form. Okay, it's got a cubic and a linear, and if you'll notice, you don't see anything squared up there. So what graphing forms are, you take maybe 3 tug-of-wars, numerical tug-of-wars, and you basically write them as fewer numerical influences. Fewer things to consider, hopefully, is a simpler way of considering something. Okay, one of the major goals of a good math education is to help people learn how to simplify more difficult things into an easier way to look at things. Okay, it's one of the major things we do in math. So I want to talk about rates of change, because that's what calculus is about. Calculus is about how rates affect amounts, and how amounts, determine rates in tabular change. So let's just look at how things change in a table from -2 to -1 to 0. Well, I get a numerical answer of -8 to -1, which is actually the numerics are going up at a 7-to-1 clip on average. In other words, over here from -8 to -1, I've gone up 7 units, right? I've gone up 7 units. And then from -1 to 0, I've gone up 1 unit. From 0 to 1, I've gone up 1 again. And from 1 to 8, back to 7. I think we get a sense that we're always going up, except right there at 0, right? And I kind of looked at that a second ago on the other board, right? There's not much change. I mean, we can get a sense of the rate of change over a small little interval, right? And still pretty close to 0. It's not, and at 0, is pretty flat, right? Pretty flat. And so the linear function is always going down at 2 to 1, from 4 to 2, from 2 to 0, 0 to -2. This is always going down at 2 to 1. So I want you to consider is what would happen if we just looked at rates of change. This is going up, at 7 to 1, it's coming down at 2 to 1, roughly. At some point, the cubic is going up at 0, and we're still going down at 2 to 1. So, up 7, down 2. Up 1, down 2. Up 1, down 2. Up 7, down 2. Tugs of war can occur with rates too, right? So who wins out here? Oh, well, somewhere in this vicinity, we're still going up. Who wins out here in terms of if you're pulling back at 2 to 1, over here, you're pulling up at 1 to 1, think about where that flag would be. Looks like you're going down. You were going up, but now when you add these two things together, you're going down. So what I'm suggesting is somewhere in here, you're turning. All right? If you put these two influences together, you're going to get a turn. You're going up, then you're going down. And certainly the one at 0, if you're not changing at all, then at the origin, you're going down this linear component, right? You're going down at that rate, -2. And that we just studied and looked at on the other board. Okay. But then, the winner again, going up. So adding these two graphs is going to get you something like that. Okay, so we can see the linear component at the point of inflection. I mean, this is the point of inflection right here, right? Where it goes from concave down to concave up. And we can study that at the pre-cal level. I mean, I haven't done any derivatives here or anything else. I'm just looking at a couple of graphs, which we study at the pre-cal level. Now, what would happen if we had x cubed plus 2x? Well, that's always going up. This influence, numerical influence, is always up. And so I think you'd see that we actually just have something that goes up faster. And you can start to get a little feel for what the graph looks like if you take a cubic and put it in graphing form. So for instance, if you knew how to put it in graphing form, would you be able to envision what this graph might look like? So I'll just write something at random. 2x minus 5 cubed. I'm running out of room here. Let's get this to be, how about minus 10 x minus 5 plus 7. I love the number 7. Yeah, everybody likes 7. Lucky 7. Except if you go to a casino and you never see it. But that's okay. I don't go to casinos. All right. So what would this look like? It's got a cubic that's positive cubic. So this is going to pass through. If you put a 5 in, you get a 7. If you put a 5 in, you get a 7. So over here, you got a 5, you get a 7. So I'm probably making this way too big. Yeah, I probably am. All right. So remember what I just did. 5, 7 right there. Okay. Oh, what are you doing at that instant? Going down at 10 to 1. But eventually, who wins out? This term wins out. So I won't write this because I really don't know where it turns. But I darn well know it does something like that. Okay, again, this is giving you information about rate of change at the point of inflection. And now what are you doing to study that? At the pre-cal level, this 5, we've talked about in class, is minus b over 3a. And just as a reminder of where that comes from, the 3 roots of any cubic, you add them up, divide by 3. There you go. Okay, wherever something, for instance, if I have a cubic at 2, at 4, let me get 6 and 12, 18, and 12, right? And I'll take it to be a positive cubic. We add 2, we add 4, we add 12, divided by 3, we get 6. Okay, so let's draw a cubic that goes through those values. Is it plausible? The point of inflection right there is 6. I hope so. Okay, so I don't think too many people know that that's where the A term, what's not with the A term? It's the X value of the point of inflection. Y, geometry. Again, it's geometry. Okay, if you had, this is all in different videos, but since we're knocking it out here, if you had X minus 2, forget the A term, X minus 2, X minus 4, X minus 12, then you have created the longest side is X minus 2, X minus 4 is the next longest. You've got that one, and X minus 12 is actually the shortest side. I'm just going to draw something like this. X minus 4. All right, boom, boom. Oh, God, I'm no good at this. There, not too bad. X minus 2, X minus 4, X minus 12. Right? And what are you doing? You're reconfiguring it. You're reconfiguring it to be an X minus 6, X minus 6, a perfect cube. Just like they have the term for quadratics, completing the square. Yeah, a square is a special rectangle where all the sides are the same. No difference in terms of how this is built. It's just all the sides are the same. And therefore, what happens at X minus 6 cubed? You get the same thing that happens at X cubed. The minimum rate of change is 0. The closer you get to 6 in this drawing, the more the volume collapses in terms of magnitude. And that's where the rate of change is either a maximum or a minimum, depending upon whether you're talking about an A term that's positive or negative. That's what's going on. Okay, and that's what I'd like to analyze and talk about over the course of the rest of the trimester that we have left. Occasionally getting into, not just the mechanics of calculus, but what it's built on, what it rests on. And if you can get an understanding of that by the end of the term, even a glance into it, I know how long it took me to visualize what's going on here. Nobody can expect the student. I don't think you can expect students to get that in a couple of months of study as you're jumping from topic to topic. But I want to keep talking about this. And I'm sorry for the artistic problems. I stopped taking art in the 3rd grade. So, but we'll keep drawing it in repetitions, my friend. So maybe I'll get to be able to explain this in a more coherent fashion as we go along. All right, so much for that one. I'm going to upload it, and I'm going to put it on there for you.